Okay.
Excuse me, can you start the talk without introduction? Maybe you can move the discussion outside later. Thank you.
Oh, thanks, Javi. So yeah, today I'll be talking about our work on this performance portable numerical relativity module within AthenaK. So this work is mostly done in collaboration with Jacob Fields, David Radice, Jim Stone, and other members in the Penn State and Jena numerical relativity group. So the outline of the talk will be the following. So first, I'll be introducing, giving you an overview of the landscape of numerical relativity with the emergence of these exascale machines. And then I'll be talking about the numerical relativity solver, in particularly like the vacuum solver, which we use the Z4C formulation. And I'll also give a brief overview of the Valencia GRMHD solver we have. And lastly, conveniently, we put out like a tutorial and GW150914 reproduction paper like yesterday on arXiv. So I'll run you through some of the features we have and diagnostics tools. Okay. So like a recent change in the numerical landscape, computational physics landscape, is the emergence of the exascale. So now there are these two exascale machines up and running. And these are like orders of magnitudes faster than the traditional CPU machines that we've had. So, things will probably not stop there. Like these massively parallel machine will, only grow at this point, and probably zettaflop machine will be here within a decade. And then it's up to us as numerical relativists to see what we can do with resource of this scale. So for the binary black hole or the vacuum problem, like one particular thing we can look at is to target it at these large mass ratio. So when you have an unequal mass ratio, then it increases the scale separation further in the binary black hole problem, and then hence your computational resource, and it scales as mass ratio cubed. So it's extremely challenging to push to some of the higher mass ratio, and for many of the surrogate model, we lack simulations for this larger mass ratio. And on the right, it's just like a proof of concept run I've done like last year with AthenaK. It's a head-on infall of a 1:20 mass ratio, and it's done on 64 GPUs on the Promuter machine on with A100 NVIDIA GPUs. And we get roughly 20 M per hour on these 64 GPUs. But then with with thousands of GPUs, we can, of course, push to much larger mass ratio and have a longer in-spiral waveform. And another region where we lack numerical relativity simulation is near extremal spin. So this is already challenging at the initial data level. So with the standard Bowman-York initial data, which assumes conformal flatness, the spin of the black hole saturated at around 0.93. So to go higher spin, like you can either lift the the conformal flatness assumption, what the RIT group does, or just use the conformal sin sandwich approach, like for example from the SXS collaboration. So now I'm working with the SXS collaboration to port over their initial data from their Spectre code, which is which uses an elliptic DG solver. So we can now read in the data from Spectre, which can be like very rapidly spinning. Like I think they've tried like 0.998 spin in spiral of equal mass black holes, and then we can also just evolve that data within AthenaK. So in the puncture gauge, like the challenge then becomes that the size of the horizons shrinks as you go to higher and higher spin. So you also like need a lot more resolution compared with slower spinning black holes. And so we're in here, like importing over the data, we're just filling the interior of the black hole through extrapolation. So originally, we have large violation of the Hamiltonian constraints inside the horizon. But then since characteristics are pointing inwards, then those flows to the punctures and then get dissipated. So another thing we can do is for like less of the more extreme parts is that we can just do more thorough sampling of the parameter space for building surrogate models. So now we have only have a couple thousands of numerical relativity simulations. And on these exascale machines, we can just do parameter scans like hundreds of binary black hole simulations at once and fill in the parameter space very quickly. So aside from building these waveform models, one of my personal interests is to study specifics of the black hole ring-down phase. So on the right, I'm showing some work I've done with the SXS group and some folks at the CCA on the excitation of different quasi-neural modes in processing system. So here we've shown that the ratios between the different spherical harmonic modes, in particular the different M modes, are actually dictated in this procession system by like kind of a misalignment angle between the orbital angular momentum at the moment of plunging with the remnant spin axis. So you can think of that as kind of a rotation of the perturbation for the remnant black hole that induces like a change in the different mode excitation. But then, as you can see, there's a lot of restructuring in this, and then to do more, and we picked out this rotation effect as the zeroth order effect. But to study more fine structures, there's mass ratios and different like original spin for the original spin configurations for the binary and so on. And to do this more systematically, we would need to do more targeted numerical relativity simulations. So, and when we move beyond vacuum, as Maitreya already talked about, we can incorporate more physics with abundance of computational resource. In particular, we can add like fluid, like magnetohydrodynamics dynamics, and couple that to our relativity, Z4C solver. So what's shown like on the right, it's the first numerical, to our knowledge, the first binary neutron star run on GPU. And then here it's a simple polytropic equation of state and no magnetic field at the original time. And then you see the two neutron stars in spiral towards each other, touching surface, creating a shearing layer. And then through various sorts of instability, transports the angular momentum outwards and finally collapse and form a black hole. Yeah. And so in this problem, like a binary neutron star or like supernova, like neutrino, as Maitreya mentioned, plays a key role. Like we are also working on like incorporating all those sort of neutrino transport and radiation transport in some for some other scenarios to model the physics more correctly. Okay, so the challenge, of course, with these exascale clusters is their heterogeneous architectures. All these large machines like run with different proprietary like programming model. Like the AMD uses HIP, Intel uses SYCL, NVIDIA uses CUDA, and then there's also like these ARM processors that just use the standard C++. For us in academia, it's incredibly costly to write different versions of your code targeted to different proprietary languages. So that's why we use COCOS, which is a performance portable programming model, which basically provides abstraction and serves as a translation layer to different sorts of backends. Okay. So with that, I'll move to introducing the numerical relativity sectors in AthenaK. So we have these three method papers. The first one has been led by James Stone and Patrick Mullen, introducing the hydro MHD radiation and the non-dynamical GRMHD harm-like solver. And then we have this second paper, which I'll be talking about mostly on the numerical relativity solver using the Z4C. And also like this paper by Jacob Fields, like on the Valencia GRMHD. Okay, so without further ado, we use the Z4C formulation. So we do a 3+1 decomposition of the Einstein equation augmented with additional vector fields. So this has a nice property compared to BSSN that we don't have zero speed for the constraints, for characteristics for the constraints. So everything is nice and propagating. and then this also like have natural incorporation of an explicit constraint damping scheme. So like this, well, we also have the evolution variables are also conformally rescaled to be compatible with puncture scheme, so we do not need to do excision, which improves parallel efficiency, as we do not need to do like a horizon finder to find the excision surface. So for the numerical implementation, we use block-based octree AMR. So we divide our computational domain into these little mesh blocks that are not overlapping with one another. So each of these blocks, like it's like basically a Cartesian mesh block, and these are like it can be either 32 cubed, 64 cubed, or 128 cubed, depending on our specification. And then and they communicate with the neighbors through ghost zones. So we implemented second, fourth, and sixth order finite differencing, which corresponds to using 2, 3, and 4 ghost cells, because we need an extra ghost cell for the advective derivatives for the shift terms for stability. For the time integrator, we use like a family of Runge-Kutta schemes. And for the RQ4 specifically, we use like a low storage variant, because on GPU we are limited by VRAM. So basically we are taking one more stage to save on one memory register. So the adaptive, so we also use this adaptive mesh refinement framework. So basically the user can specify some type of refinement criteria. Here, like we can either use the puncture location or the conformal factor to specify refinement for this binary black hole problem. And lastly, we use a task-based parallelism. So now we have basically like a domain of mesh blocks, and then these are ordered by some Z ordering, and then those are then broken into chunks and put into each MPI rank. So for each MPI rank, we have a list of like tasks, including like, for example, calculating the right-hand side, like communicating, doing like prolongation and restriction if you have adaptive mesh refinement, and then communicate with its neighbors like through MPI send and receive. And then each rank like navigates through this task like independently, and to basically improve on parallel efficiency. So like the main kernels like in our solver are just ported over from the GR Athena++, with the major difference being that we use a different scheme for the grid discretization. So in GR Athena++, we mostly use like the vertex center scheme. So this is showing one mesh block where the little circles are locations of the cells for the actual like evolution grid, but then it's communicating with the boundaries with its neighbors using these coarse buffers, which is at 1/2 the resolution shown by these larger circles. So in this vertex centers, the advantage is that basically like you saves on like a restriction operation, namely that these like core cells, like you can fill them for free, like as they coincide with the finer resolution cells. But then when you couple with the fluid solvers, which are saving, which are basically the cell average saved usually at the cell center, then you need to do an extra interpolation to the cell centers for the for the vertex centers variables. So in the AthenaK, then we actually just choose directly do like a cell-centered, evolve the cell-centered finite differencing scheme. Okay, so we have done a bunch of tests, one of which includes like a binary black hole evolution with AthenaK. So we use the BAM calibration run. So this is only a 3 orbits, like equal mass non-spinning. And here, like I'm just showing a video of the mesh structure during the course of this evolution. And then we extract the gravitational waveform at finite radius, and we calculate the well scalar. So we run our code at 3 different resolutions, differing by factors of 2, and we observe like a fourth order convergence, which is consistent with the RK4 scheme that we are using. So we also compare with the same initial data. We compare with the GR sinus++, and then we find convergence, although with different grid structure and refinement scheme. Okay, so another another thing one want to explore with the to achieve accurate numerical relativity waveform is with the AMR. What is the best strategy to do to specify your grid structure for refinement? So as similar to like these finite element scheme, if you view the different mesh blocks as computational elements, you can either do like a P refinement in which like you basically increase the number of points inside the mesh block, say replacing like say 64 cubed by 128 cubed, or you can just do a global refinement, like basically by dividing the mesh blocks into like a smaller mesh blocks. So why we want to do that? So basically, if we have say 32 cubed mesh blocks, we can basically just increase the level of mesh refinement by one level at the punctures to get a higher resolution at the punctures while remaining the same resolution at the wave zone. And then this only increase your resolution, your computational cost by a factor of 2, because you're pretty much just limited by the CFL. The number of mesh block, the additional number of mesh blocks you increase is rather minimal. So here, like in this benchmark test, we are looking still at the BAM calibration run, and I'm showing basically the waveform error at the low resolution, like which is shown in orange. And if we basically do a global refinement, P refinement, increase the resolution everywhere, then the error we get is the blue curve. But if we locally only increase a level of refinement at the puncture, what we see, the error now we get is the red curve. So basically, like we find that in this highlighted blue region, which is the in-spiral region, we find that the error, like from this, which is from this by increasing level of refinement, is more or less consistent with a global increase in the resolution, meaning that in this phase, the error is just dominated by the resolution at the puncture. At the early and later phase, like either the error is dominated by like just the junk radiation, which is high frequency propagating in the wave zone, or the rain-down signal, which is also a lot more higher frequency. So ideally, like we would want to do this type of H refinement, putting more resolution at the puncture during the evolution, and maybe at the rain-down just do like a further refinement in the wave zone to capture these higher frequency signals more accurately. So, okay, so our code is tailored towards performance portability. So far we have run it on a variety of hardwares, ranging from GPUs to CPUs, including like vendors from NVIDIA, AMD, and Intel. So comparing like with this with the kind of the last gen NVIDIA mainstream A100 GPUs, we are getting like for the Z4C solver, we are getting like a factor of a few hundred speed up compared with some of the mainstream CPU used in the HPC. Okay, now to scaling test. So we aim at running on these exascale machines. So weak scaling is important. So basically, in scaling up the computational resource, we also like scale up the problem accordingly. So here, like we have done like weak scaling tests on both Frontier and Aurora, which uses AMD and NVIDIA and Intel GPUs accordingly. We have run up to around almost 10 to the 5 GPUs, and we observe like a weak scaling efficiency of like roughly 80%. with like 64 cubed mesh block. So, and so another important thing is, of course, human time. So we care about wall clock. For this test, like strong scaling is important. So we are keeping the problem size fixed while scaling up the resource. So here, like on both frontier and perlmutter, we are saturating the resource at the smallest number of GPU and then just scaling up. And we find that like increasing like the number of GPUs by 32 times, we still get roughly a 80% scaling efficiency. So yeah. Any questions so far on the Z4C solver before I move on? Okay. So if not, I'll give a brief overview of the Valencia MHD formulation we've implemented. So the Valencia GRMHD comes from just the 3+1 decomposition of the ideal GRMHD equations. We solve these set of equations using like a constraint transport scheme on a staggered grid. So we basically evolve the magnetic fields on the faces and electric fields on the edges of the grid. So this prevents the needs of doing divergence cleaning, and so the DB constraints are preserved to machine precision. So for the Riemann solver, we have we have implemented LLF and HLLE. We have the reconstruction implemented as part of the rest of the AthenaK. We have like a donor cell PLM, PPM, and also like extrema preserving PPMX, and also we know Z implementation. So one thing that's slightly different from some typical treatment is how we treat the atmosphere. So usually, like when a constant prime inversion fails, people just floor it to say if you get a negative energy density or so on. So we still do flooring, but before that we also have a first order flux correction to basically try to preserve the conservation loss better, because if you do flooring, you're basically injecting energy and mass into your system and removing momentum. So this first order flux correction works as the following. So we basically calculate the flux and then estimate like a Runge-Kutta update. And if that indicates a failure in the constant prime, then we flag those cells and then we refold back to a more dissipative methods. Basically, we just use the donor cell and the LLF, which is positivity preserving. So this doesn't eliminate the needs for flooring, but it reduces the amount of flooring we need to do due to spurious oscillations near like these discontinuities like star surfaces and so on. And then so in this binary neutron star evolution run, we are showing basically the mass conservation compared with the implementation in GR++, which doesn't use this first order flux correction. So these LR, SR, HR are just like successively higher resolution in AthenaK. And we find that that we get like a couple orders of magnitude better mass conservation in these binary neutron star runs. And at the late time, like all of these have strong violation. That's just because a black hole has formed and causing excision. So the conservation breaks. So in addition to first order flux correction, so usually before the constant prime inversion fails, there's already some unphysical oscillations in your system. So as an effort to predict this and remove these unphysical oscillations as much as possible, we also have a discrete. We also enforce like a discrete maximum principle. Basically, in a scalar advection, in a scalar conservation law, you have like a maximum principle, and in this case, for the GRMHD equations, these are not exact, but we just enforce that if the the self-centered variables is not within like these maximums of its neighbors, within some tolerance specified by M, then we basically trigger the first order flux correction to have a more dissipation to avoid the more unphysical scheme. Though in the binary neutron star test, we have not used this. Okay, so some more testing. So you can refer to Jacob's paper for more of the basics testing, but here I'll be showing mostly just tests involving a neutron star. So so first we evolve like a neutron star in Calling approximation. So basically we are freezing the metric variables, so we're not evolving space-time. So it's a TOV star with some perturbation. So here we are testing our scheme for like the first order flux correction, as well as this first order flux correction plus the discrete maximum preserving principle, and then comparing to the black lines, which are just without these with the standard atmospheric treatment, and then we find like consistent in the density variations at the start center. And if you take a Fourier transform and calculate the spectrum, we see that these peaks at the expected mode frequencies of the neutron star. And in the second test, we now no longer freeze the metric variables, but then we're no longer adding like a linear perturbation. So here it's just purely just numerical. So we are evolving both the space-time and the matter. And then we're still finding consistencies between these schemes, which is expected because these first order flux corrections would only happen like with constant frame failures. Okay, and so furthermore, we do like a binary neutron star evolution. So these are with a polytropic equation of state and known magnetic fields. And we are comparing with some previous runs with a whiskey THC as well as the GR acetylphosphate. So in the waveform, like we are running at 3 different resolution, and on the top panel, like which is the string from fixed frequency integration, we are seeing consistency between all these codes. After merger, like but in the later stage, then these codes diverge, which is a well-known problem, and then in evolution of neutron stars, and then leading to collapse also at inconsistent times. And within the AthenaK, we are finding a second order convergence in the waveform, which is shown in the phase difference between the different resolution runs, which is consistent with the scheme that we are using. So any questions so far? Okay, so if not, I'll talk about like just give you a walkthrough of the code and point you to some of the tutorial we have built up. So in a recent paper led by David, like we have reproduced the GW150914 simulation and compared with the runs in a previous paper led by Jeffrey Lovelace and others, like with the SXS group and the RIT group. So so we have this GitHub page now that's available that guides you through like compilation of the code and so on. I'll just walk you through this briefly. So this is basically like a overview and tutorial of how to run binary black hole simulation with AthenaK. So for the initial data, we use the 2-puncture code. Which also requires the GSL library, and you can find the detailed compilation guides like in the AthenaK's wiki page. So this runs us through like basically the compilation for the Z4C 2-puncture problem. And we also provide like a input file for this for our code for this particular run. And we generate the initial data like at runtime. So basically, we at the start of the run, like we run the two-puncture code on CPU and then just interpolate the data from their spectral grid to our Cartesian grid. And here we are specifying basically the number of points in the mesh block, and we're in our domain, we're doing the refinement. So again, we used like a block-based AMR. So here, like we basically just put a box of refinement near the punctures, and our AMR structure requires a 2-to-1 refinement ratio. So it leads to like natural cascade of resolution into the wave zone. So in addition to refining the puncture, we also set a minimum number of refinement, like on a larger Cartesian box, to ensure that the wave zone, like the region where we extract the gravitational wave, is also properly refined, so that we don't get aliasing in the waveform. So for the diagnostics, we provide the puncture structure, where you can which is just done by just integrating shift along the puncture's location. And so this is like the puncture trajectory for the first couple segments in our run. And furthermore, we have a apparent horizon finder thanks to provided by Zach. So what we do is that we dump a Cartesian box of the ADM variables centered on the puncture, and then this is then read into like a minimal built version of the Einstein toolkit that contains the quasi-local measures as well as the fast horizon finder by Sundberg. And then this gives us basically the horizon quantities and including the mass and spin of the black hole. So for the gravitational wave, like we have two methods for doing the extraction. The first one is to do like fixed radius extraction. We do that just with geodesic spheres, breaking into spherical harmonics at different set radius. And then one can extrapolate this to future null infinity using or infinity like with the standard techniques. So we also provide like a Cauchy characteristic extraction. So we basically dump the variables at a finite world tube. I'll talk more about this in the later slides. We dump the VDM variable and their derivatives on the world tube, and then we use the Spectre CCE module, like in Deborah's talk, to get the waveform at the scry, and then this captures all the correct fixed physical quantities like the gravitational wave memory, and then one can also just do more consistent test with less gauge ambiguity by fixing the BMS charges. Okay, so now going back to some of the results in this paper. So again, like going back to the CCE, so we basically obtained the initial data on a Cauchy slice and out to some like outer boundary of our code, and then evolve it forwards in AthenaK and dump the data on world tube. So here, like because the CCE requires the radial derivatives of the different metric variables, what we do instead is that we dump on like some concentric spheres, and then on each sphere we are dumping the spherical harmonic decomposed components for say the metric and the alpha and the beta. So these spheres are located at these like Chebyshev collocation points, and later on in a post-processing script we take the radial derivative that way. And then the time derivative we are calculating through just like a Fourier transform globally. So okay, so here are some of the waveforms that we are getting through the Spectre CCE. Some of the dominant modes, including the m = 0 modes, where you can see the memory is more pronounced. say in the 2-0 modes, as well as the more dominant like L equals M modes, like the 2-2 modes, 3-3 modes, and 4-4 modes. And we have then since compared with SXS and the RIT group on the 2-2 modes amplitude. So on top we are plotting our waveform on top of the SXS and the RIT waveform. And in the bottom we are showing like the phase difference as well as the fractional amplitude difference. And overall we find that they are quite consistent. Though in looking at this plots, you see these like wiggles like in the phase difference. And after Deborah's talk, I actually looked a bit like at the junk radiation in the CCE region, and found that much of that is probably attributed to that. So here, like on the left, we are showing like a finite radius string like that we calculated through like a fixed frequency integration. And then you can see that the amplitude for this 2-2 mode is very smooth, and it doesn't seem to be affected by eccentricity. But then in our CCE run, we see this wiggles all the way almost up to the time of merger. So again, like maybe adjusting the time window for doing the padding time for doing the frame alignment would mitigate much of these unwanted oscillations. So yeah, so with that, I'll conclude the talk and take any questions from now.
So on that last plot, this is more of a comment. Well, it's slash question. Did you try doing this with multiple initial roll 2 radii?
Oh yeah. So the question was that like, have we tried CC at different radii? We have not done this yet.
Showed you guys the best plot. I had some of the radii. I had a really hard time finding a window for the frame that made the wiggles go away. So it's definitely possible that a different radius might help mitigate the wiggles as well.
I do agree, and we are doing we are also doing this at a much like smaller radius, like at r equals 50. So I think this might be too small. Yeah, I guess maybe like I think like I was talking with some of the SXS folks, and they are kind of suggesting around 150 or something like that. But then it's always like, there's always that, when you go out further with a Cartesian-based code, like your resolution cascade like very fast. So yeah, we need to do more systematics investigation to find out what's the optimal balance. Oh yes, Zach.
Yeah. So a couple questions. First, in your very high spin evolutions that you showed very earlier on, so punctured black holes have a tendency, even if they start out spherical, to kind of pancake in perpendicular to the direction of the spin vector. Do you have any ability to refine in sort of a pancakey like shape?
Yes. So basically, like we have this refinement. Oh yeah, sorry. So the question was that so in this like highly spinning black hole, like they become like more pancake and more oblate. So and can we have like mesh structure that's adapted to this, like have a refinement? Well, I guess less on the z-axis, but more like on the x and y axis. And it is and the question, well, the answer is yes. So we have this additional like refinement criteria basically based on, say, the conformal factor, for example, which is like proportional, well, some power of the determinant of the spatial metric. So basically we can set, if it dips below a certain value, then we refine it, and then that can be more adapted to the geometry, like for either just highly boosted black hole or like in this case, like very highly spinning black hole. Yeah.
Cool. In the wave zone, are there plans to use something more akin to a spherical coordinate system?
Oh, not yet. There's no plan of adapting like spherical coordinate like in AthenaK. Yeah, but in principle, like you have a multi-patch, like it would be a lot more, a lot cheaper because then you just have a linear scaling in the resolution in the wave zone.
Hey, so can you go back to that slide where you described the advantage you guys have by using cell-centered quantities for your space-time evolution? I didn't quite understand that. Where the advantage is coming from doing cell-centering instead of vertex-centering for that?
Oh, yes. So the question is about like why we're using cell-centered versus vertex-centered. So basically, like the fluid variables, like are yes.
For the space, so for the fluid quantities, I understand why you want cell-centered, but for the space-time quantities, I understood that you found that there is an advantage having those quantities as well be cell-centered.
Oh, so well, just comparing with vertex-centered and cell-centered for like just vacuum space-time alone, like the vertex-centered is the more optimal choice, right? Because you have like just better symmetries, like in the interpolation stencils and so on, and also like you save on a number of operations. So we choose the cell-centered specifically just for easier coupling with the GRMHD because. In this case, like, you need to calculate the source terms for the GRMHD, which are now just conveniently located at the same location. And also like vice versa, when you calculate like say the stress energy tensor, then they will be at the same location. So that will be a lot easier.
Do you have the ability to have these two different kinds of variables centrally working together in the simulation? Or pick one from that?
Yes, we need to pick one and go with that. So I think in GR single plus they have since then also implemented the cell-centered. So I think they can just choose between like vertex-centered and cell-centered. But in AthenaK, we only implemented like the cell-centered so far.
Well, I actually brought a question to my mind. So when you're doing cell-centered, when you're doing the restriction, I mean, the simplest, of course, is just to take the average of the cells that are in there. But do you need to do something else when you go to higher finite difference order?
Yes. So actually here, like we are using just like a Lagrange interpolation to do the higher order Lagrange interpolation to do the restriction as well as the prolongation. So one of the caveat is that it is like it's kind of an asymmetric stencil, but so far like we haven't found any stability issues related to that. So it doesn't seem to be the dominant cost of anything. Yeah.
I believe we would resist the question.
Oh, yes. So Li Wei, you have a question?
Yeah, great talk. So could you comment on the cost of all these analysis module, say the gradient wave and also maybe a that what percentage of the simulation time it takes compared to the true evolution?
Oh, you mean the cost of the diagnostics compared with
Right.
evolution?
Right.
So yeah, that is a great question. I haven't estimated that quite yet. So for the JW15 0914 run, we are getting like roughly, I guess 7 times 10 to the 8th zone cycles per second on like 32 nodes on Aurora. And then like I guess, and that is with all the full diagnostics with CCE and dumping data for horizon find and finite radius and puncture tracker and so on. Oh, well, I think that might also include like saving restart from time to time. And I think without those diagnostics, we get like roughly like with the same amount of GPUs on the same machine, like we get a bit over 1 billion zone cycles per second. So maybe the diagnostic cost would be somewhere between 30 to 40 20, well, 20 to 40%, I would say, of the total computational cost.
So when you say that you down the data to use the advanced finder, what do you mean? What kind of data did you dump?
Yeah, so we basically just dump like a Cartesian box centered around the punctures.
Oh, okay.
We dump the ADM variables, which are then just read into like a minimal built version of Einstein toolkit, and then we just run the AH find direct.
Okay. Thanks.
Yes.
I'm just quickly showing the GitHub.
Oh, yeah.
Get this.
Yeah, of course.
Well, then,
Excellent.
I'll speak again.
Thank you very much.
That's the end of this session, and they.